Welcome to another physics lesson. Today we'll be looking at energy quantization. By the end of this lesson, we should have been able to explain the concept of energy quantization, and we should also be able to solve simple exercises on energy quantization. So let's get started. What exactly do we mean by energy quantization? And where does this important topic arise from? Now, we have different scientists who worked at different times to postulate what an atom looks like, starting from Dalton's atomic theory to John Thomas to Rutherford, and then we have Niels Bohr, who also had a postulate of the atom. So what Niels Bohr said was that an atom consists of electrons that move around the nucleus in specified orbits. And these orbits the atoms move without radiating any energy. That means that they acquire or lose energy only in discrete units called quanta or photon. What do we mean by discrete? Discrete means that the energy that we are talking about that an electron will have to acquire or lose in order to change its energy state is a specific value, a discrete value. It is not a continuous value. In other words, we are saying that for an electron to leave the state it is in, it must possess that specific amount of energy. It's either it has that amount of energy or it does not. There is no middle way. There's no way, and you cannot say that an electron has only part of the energy it needed to change state, and then it now left its present shell and then got in between two shells and then got hanging. No. It's either the energy needed is complete, discrete, or it is not. So these units are what we call discrete units, otherwise called quanta or photon. Photon, as we know, stems from light, and photon is used here because the energy we are referring to is the energy given by light, incident light on an atom. Bohr then suggested that electrons in the atom exist in discrete energy states. And that is where the term energy quantization comes from. Energy quantization means energy in discrete values, discrete energy values, not continuous. So each atomic shell has the specific energy value that it possesses. The energy value that an electron trying to move into that shell or move away from that shell must possess. That is an important postulate of Bohr, and that's the genesis of this topic, energy quantization. Another scientist, Max Planck, continued from where Bohr stopped and showed that radiation emitted by substances could be explained on the basis that the energy from such bodies is emitted in discrete packets, known as the quanta, as I said earlier. Now, Max Planck then derived the equation E equals hf for that energy, where h is Planck's constant. H is Planck's constant, and f is the frequency of radiation. As I said earlier, the term quantum means fixed, discrete, or separate amount as against a continuous value. So Planck's quantum hypothesis says that energy of radiation can be E equals hf, 2hf, or 3hf. 1, 2, and 3 there being the number of energy levels that you have. But it cannot be anything in between. It cannot be half hf or 2.5 hf or 2 to third hf. No. It cannot be anything in between. It has to be energy emitted or possessed in discrete values. So energy radiated by electrons is therefore not a continuous quantity, but is quantized, existing only in discrete amounts. Quantum energy is measured in electron volts. That's the energy gained by an electron when it accelerates through a potential difference of 1 volt. That's the electron volt. There's a conversion between the electron volts and the joules, which we will see later. Now let's talk about energy levels. As I said earlier, electrons are arranged around their nuclei energy levels or shells, as we know them. Electrons are held in this orbit by the force of attraction between the electron and the nucleus. So the electron keeps orbiting in this specific shell due to the force that keeps it in that orbit, the force of attraction between the electron itself and the nucleus. Now the electrons in the energy level closest to the nucleus or in the shell closest to the nucleus have the highest amount of energy. That's why it will take more energy to remove such electrons from their shells than for the energies at other energy levels. So the amount of energy needed to remove electrons from energy levels decreases as the distance of the energy level from the nucleus increases. So that means that the electron closest to the nucleus will require the highest amount of energy to remove from that shell. The one next to that, the one in the next shell or the second shell to the nucleus, will require a little less energy than the one closest to the shell to the nucleus required. Now, the electron in maybe the fifth shell to the nucleus will require far less energy than those ones that are closer to the nucleus required for them to be removed from their shells. Just for illustration, we can see here what the model of the hydrogen atom looks like. This is as worked on by Bohr. We have the different energy levels, n equals 1, 2, and 3. So the electrons in the first energy level will have the highest amount of energy, while the ones in the second energy level will have a lower amount of energy, and the ones in the third energy level will have the lowest amount of energy based on these shells. Now, these shells or these energy levels are the only allowed energy levels for an electron to orbit. There cannot be anywhere in between where you can have electrons. Electrons cannot be in between 1 and 2, for instance. They have to either be on 1 or on 2. As again said earlier, that is what the whole idea of discrete energy or quantized energy means. If you also look at the second diagram, as I said earlier, we have the amount of energies closest to the nucleus being the highest. So here now, for n equals 1, we can see 13.6 electron volts, and the value continues to decrease as the number of shells or the energy levels continue to increase. Now you may be wondering, why do we have the negative signs in front of this? The negative signs actually do not affect, they are not magnitude signs. So it's not that the electron is minus 13.6 electron volts. No, it's just that the work done, the work we are doing here, the energy possessed there, is the energy that is done on the atom, not energy done by the atom, or energy done on the electron. That's what that negative refers to. In calculations, it won't affect your calculations in any way. And as I said earlier, I said there's a conversion scale for electron volt to joules. You can also see that on the lower rank of that diagram. 1 electron volt equals 1.6 times 10 to the power minus 19 joules. That's how to convert electron volts to joules. Keep that in mind. The electrons in the closest orbit are therefore the ones that are most stable. The closest orbit to the nucleus, they are the ones most stable. But when an electron is infinitely far from the atom, is maybe on an infinite shell, very far from the atom, or is completely removed from the atom, then the atom is said to be ionized. The energy of this infinite level is therefore 0. So that means that while the energy possessed by the electron closest to the nucleus is maximum, the one possessed by an infinite electron on an infinite shell very far away from the nucleus is 0. When an atom is heated or bombarded with an energetic particle, its energy is increased and the atom is said to be excited. For the atom to be excited, its energy must be increased by a definite discrete amount. For the atom to be excited, the energy must be increased by a definite discrete amount. No intermediate energy change is possible. So during excitation, that's when the energy of an atom is being increased. One of the electrons may move to a higher energy level, but excited states are unstable. So when an electron moves to a higher energy level, it is unstable in that energy level, it soon jumps back to its original orbit, and then it emits a photon or a quantum of light with a frequency f in that process. Now, this is given by the relation delta E. Delta E is actually difference between the energy levels of the two states in question, the one the electron was at before and the one it jumped to. So delta E, that's caused by En minus E naught, where En there is the energy level of the other states that the electron jumped to, and naught there, E naught is the energy level of the original orbit of the electron. E or delta E equals HF, as we said, HFN. Now remember that from our speed of light equation, C equals F lambda. So that means that F is C over lambda. That's why we said HF can also be equal to HC over lambda. Now, not all electrons jump to the ground level. Some jumps are between other energy levels apart from the ground energy level. So as I said, the difference is the delta E is just different between the energy level that the electron was at before and the new level it jumps to. In rounding off, let's see an example. An electron jumps from one energy level to another in an atom, and then it gives us 4.5 times 10 to the minus 19 joules of energy. Now we have Planck's constant, that's 6.6 times 10 to the minus 34 joules seconds. What's the wavelength of the radiation? Velocity of light is 3 times 10 to the power 8 meters per second. That's also a constant value. So as I said, delta E equals HF. So find the delta E. You had already been told the energy radiated by the atom. That's the delta E. That means that when the electron jumped from one energy level to another, it gave off 4.5 times 10 to the minus 19 joules. That means that the difference between the energy levels of the two shells that the electron jumped from and to is 4.5 times 10 to the minus 19. That's your delta E. And then you are given H. We all know that our F is C over lambda. The question asks us to find lambda, so we just use C over lambda to represent F or to replace F. And we are able to get our lambda here straightforward. You can also try this question by yourself and see if you get the right answer. Now we have come to the end of this lesson. We can solve these questions, we can lay our hands on them. We have an atom excited to an energy level E2. Now you are given the specific energy levels of both shells. So here your delta E is a subtraction of the two energy levels that you have. Now calculate the frequency. You use delta E equals HF. You are given H already, you find the F. Then it says calculate the wavelength. You find your wavelength lambda by using C equals F lambda. So that means that lambda will be C over F, and you already found F. Second one says calculate the frequency of the emitted photon when the energy released during a de-excitation process is 12.75 electron volts. So now you have been given the energy release, but it is in electron volts. So you must convert to joules. Remember I said earlier that 1 electron volt is 1.6 times 10 to the minus 19 joules. So you convert it to joules, and then you find the frequency using the formula E equals HF. So this is the end of today's lesson. Hope to see you sometime very soon in another topic. Thank you.